So clearly I don't have anything better to do on a Sunday afternoon, thanks to being widowed to the Six Nations. So a few comments and questions came up from Canvas about the pseudo first order approximation. So I'm just going to cover a little bit about it, maybe go over it again in slightly different way. Hopefully this can clear things up, or it'll help you apply it a little better. So to start with, let's look at the first order reaction. So I'm just going to write out what should become very, very quick and easy knowledge to people. This is the first order reaction. So the change in the concentration divided by the change in time is equal to a rate constant, just a proportionality constant, multiplied by the concentration. Hey, this is great. This is really easy. This is the easiest sort of kinetics you can do. Now, if you were to plot this concentration here, time along the bottom, what you would find is this was a kind of, well, I can't really draw an exponential curve perfectly first time, but it's an exponential curve. Now, for reasons that will become kind of mathematically obvious as we progress, if we plot time along the bottom, and then the natural log of a concentration, or in fact any kind of log of the concentration, to be honest, you get a straight line. If I could draw a straight line again, and that gradient equals k, or at least negative k. So if we plot that data, we get a straight line. This is brilliant. This is really, really easy. But first order reactions in chemistry are in fact quite rare, or at least they're rarely interesting. I mean, come on, it's just a dissociation. They're not going to be very useful to us. So we need to look at more complicated kinetics. So now let's just imagine our rate is equal to a second order reaction. That's K times two reagents, two reactants, A and B. This is a bit harder to work out. It's you can kind of do a little bit of modeling to deal with it, but it is not immediately very easy to solve. There's more than one value, more than one variable. It's very difficult to actually get a rate constant out of this. However, a lot of reactions like this usually have one reagent in a vast excess. I mean, think about things that are reacting with catalysts, for instance. You might have our initial concentration of A. This is our reactant of some description, might be somewhere in the region of 0.01 moles, at least moles per decimeter cubed, I should say. And B might be sodium hydroxide, it might be hydrochloric acid, it might be any kind of, could even be water, in fact. It's quite common across various things. So go back over your organic notes and see where you might see this kind of thing. That could be 5.0 moles per dm cubed. Okay, that's a lot. So this reaction is 1-to-1. A plus B just goes somewhere. We couldn't care less where it goes at the moment. So that means at the end of a reaction, this 0.01 moles of A will have gone down to 0, and this will have gone down to, well, it's not 0, it will have moved to 4.99. Let me just write this out fully for a moment. So this is at the start, this is at the end, and what you should be able to spot from this is that this number hasn't changed a lot. It's changed a little bit, but that's only over the course of all of the reaction as well. For at least half the reaction, it's going to be even closer to 5 than that. So effectively, or at least within any kind of reasonable experimental error, this number here, that value, is in fact constant. Now the rate constant here, given its name, is also constant. So this gives us an idea of how we can simplify this equation now. So I'm just going to write it out fully again. and I'm going to swap the order of these around so it can just be written out a little easier. If this is constant and this is constant, then remember that whole reading equations thing. You want to take your constants and you want to bring them all in together. Just treat them as one big constant and then deal with it later. That can now simplify to another kind of rate constant. And various ways of doing this. Sometimes people call it k prime, stick a little value up there. Alternatively, we can call it k observed. That's my personal preference, k obs. And we can bring, let's see, this down as well. So as an approximation, our rate actually is this. And now this is a first order reaction. Easy, really easy to deal with. We've just covered it up here. If this is what our rate laws look like, then this is the curve the reactants make. We take a log of it and plot it, we get a gradient out. So we can in fact get k or minus k obs out of that. So if something's in excess, we can just simplify things down. Now, if we have a rate equals k obs times a, we can actually then start saying, well, what is k obs equal to? We can write that down as well. So k observed is equal to, well, whatever's in that blue cloud in the corner there, k times the concentration of B. So this is our pseudo first, and this is our actual second order constant. Okay, so now we can kind of rearrange that to get what the value of k is, bring that to the other side, or multiply both, divide both sides by a, depending on whatever your preference is. So we divide through by concentration, and that gets us k, the second order rate constant. So you can do this several times and realize that, well, that's a straight line equation. It is a linear equation, so we could plot this on a graph. For instance, we could put k obs here for various different recordings of it. Sorry, I've just realised this should be B. What was the point of me writing it out the other way? B here, and this could be a straight line. We could take it from various data points and find out a gradient from it, or we can do this equation several times for different concentrations, 5 moles, 4 moles, or whatever, and we'll find that this stays constant. This one is proportional to the concentration of the thing that's in excess. So that should be kind of it, really. Well, got a couple of minutes, I may as well give you another example. Let's think of a third order reaction for a moment. This sort of thing is very, very, I'll put it here. This sort of thing is very, very common in the atmosphere, for instance, where A might be in excess and is nitrogen or something called an inert collision partner. They take part in the reactions, but they don't necessarily react. So that's actually quite common in atmospheric chemistry. So if we have this, that's a third order reaction. And of course we have a third order rate constant in there. If that's in excess and doesn't change, this itself can actually be crunched down into a single k obs as well. So our rate then approximates, yeah, I'll keep it as approximate, k observed B squared. You can see that comes down to there, and our k obs is equal to, oops, green. Let's see, changing colour takes a while, but makes it look a bit prettier and easier to follow. Yeah, equals this. So this is called a pseudo second order reaction. And we do this because, just like the first order reaction, this sort of rate law, where it's just two things squared, is actually a kind of a special case that we can solve. It's very similar to this sort of first order behavior. We can deal with it. So what these approximations are about is trying to simplify down our theories to match the experiments we might want to do. So we put something in excess, that concentration doesn't really change. We can kind of get away with ignoring it. We can simplify things down, and it means we can solve the equations better and far more easily and intuitively. So that is what the approximations are. You find them a lot in physical chemistry, a lot in physics, and a lot in chemistry anyway. So hopefully this helps clear a few things up, and then we'll get on to really applying them.